Okay, let's go. Thank you all for registering to this introduction to statistical testing illustrated with XLSTAT. I am Jean-Paul Maalouf. I'm a statistics consultant at XLSTAT. Many of you already know me because of the previous webinars I have already run. So I'm very happy to talk to you today about statistical testing. As usual, I won't be referencing to complex mathematical formula. I'll just use an intuitive way to introduce things. So all along the webinar, you'll be able to ask questions using the chatting window. So don't use the raise your hand feature, just use the chatting window to ask your questions. And I'll stop once at the middle of the webinar to answer the first set of questions. And then at the end of the webinar, I'll answer the remaining questions. The handouts, so the presentation as well as the data, are available for download in the handouts section. So don't hesitate to download them. And the recording will be available starting from next week, this time. Usually I make it available starting from the day after the webinar, but exceptionally today I'll just keep the recording for next week. So the goal of this webinar is to let you become independent in using our WebStat test selection tool. So we have a tool online which looks like this grid, and which allows you to choose an appropriate test according to the question you have, to the data you have, to the null hypothesis you have. We'll see what the null hypothesis is. And the goal of this webinar is really to make you independent in using this tool. So you have a link to this grid by clicking here. There it is. Here we go. So according to the question you have, to the test family you have, to the data you have, you will find different parametric tests and non-parametric equivalents that you can use. You can click on them and see how they work in XLSTAT. And I really hope that at the end of this webinar, you'll be able to easily use this tool. So what's the plan? I'll first start, as usual, with a brief presentation of XLSTAT before introducing the categories in which I'm used to store different statistical tools. Then I'll switch to a reminder on descriptive and exploratory statistics. Those were the topics of the first two webinars of the season. So those of you who haven't attended them, I'll just do a small and quick reminder on them before doing the transition to statistical tests. So I will talk about the principles of statistical testing through the steps I usually use to run statistical tests, and I will show you a first example of statistical test in XLSTAT. Then I will talk about three topics of opposing ideas in the world of statistical testing. I'll first talk about parametric versus non-parametric tests. What is a parametric test and what is a non-parametric test, and what is the advantage of one compared to the other. Then I'll show you the opposition between the tests on independent and paired samples, and the opposition between the tests of comparison and tests of association. And I'll do another practice on XLSTAT, Fisher's exact test on a contingency table or on a crosstab before concluding. You have many appendices. This is the first one, so don't hesitate to check them out to have a bit more insight about statistical testing. Who are we? So XLSTAT is a user-friendly statistical add-on software for Microsoft Excel. Those of you who haven't used it already, you will see how it looks like during the demonstrations. So here's a brief historical overview. It all started in 1993 when our CEO, Thierry Famy, started developing the interface. The first sale occurred in 1996 on the internet. Then in 2000, the Addinsoft company, which hosts today the XLSTAT company, was created. In 2006, we had a new version that included two kinds of coding inside, so VBA and C++. Then in 2009, we had new offers that were rethought in 2015 in new products that are field-oriented, and we had a new website in 2015. Then 2016, we had two major releases, XLSTAT 365, which is the cloud version of XLSTAT that works on Excel 365 on the internet, as well as the XLSTAT free edition. The XLSTAT free edition includes a limited number of features that you can use for free, so without having a valid license. And then in 2017, so we just released the R integration. So R is a statistical software that works in lines of code, and that is free. And today we have an interface in XLSTAT that allows you to use R within XLSTAT and within Excel. So don't hesitate to try it. It's already online, the current version online. Don't hesitate to try it and tell us what you think. In a few numbers, there are more than 200 statistical features in XLSTAT. We are 22 employees. There are 100,000 users of the software across the world. We have 220K visits a month on the website. The software is available in 7 languages, and we have 10,000 downloads of the software per month. So statistics can be stored, statistical tools can be stored into 4 categories. So this is my personal way of grouping statistical methods into categories. First of all, we have descriptive statistics that help you summarize data using simple statistics or charts, such as the mean, the standard deviation, the box plots. So those tools are useful when you have maybe one single variable or pairs of variables or 3 variables, but generally not more than that. And usually descriptive statistical tools allow you to generate statements or hypotheses without necessarily having a precise question in your head. Exploratory statistical tools allow you to have the same kind of reasoning. So you can extract hypotheses or statements on data, but the main difference between exploration and description is that exploratory tools allow you to investigate a higher number of variables. So you can have 10 variables that you can investigate using the same tool within the exploratory data analysis framework. So we explore and we generate hypotheses using those 2 families of methods. Statistical tests allow us to accept or reject very precise hypotheses, assuming error risks. So here we extract hypotheses, but we are not pretty sure statistically if they're valid or not. Statistical tests allow us to validate or to reject hypotheses, of course, assuming some error risks. So the 2 approaches, description and exploration on one side and tests on the other, are very complementary. Then statistical modeling allow you to understand the way a phenomenon evolves according to a set of parameters. We have regression and ANOVA and ANCOVA in modeling. So there are many tools that can be found in one section and in another one. So there are no very precise limits between the families. This is just a simple way of summarizing statistical methods and putting them into groups to make them pedagogically more interesting. Today we focus on statistical testing, and there are 2 webinars in the coming month on modeling and on ANOVA. So modeling, on general modeling, and on ANOVA, which are both part of statistical modeling. Here you can find links to the recordings of the first sessions, so description and exploration. You already have had 1 webinar per topic. Today we focus on statistical testing, and here you have links to subscribe to the upcoming webinars on modeling and ANOVA. So I hope to see you there as well. Here's a small reminder on descriptive and exploratory statistics, so on the topics of the first 2 webinars of this season. We talked about this data set, so most of the webinars content were based on this data set, which is the client database from an online shoe selling platform. So here in rows you have individuals, different clients, who are described by several variables. You have the origin, the gender, the height, shoe size, weight, and so on. There are qualitative variables such as origin, gender, and quantitative ones such as height, shoe size, invoice amount. So we investigated many tools, many statistical tools that let us describe variables on themselves, so single variables, and pairs of variables, whether they were quantitative or qualitative. But I want to focus on one specific tool we investigated at the end of the webinar, which is the scatter plot. So, which illustrates the link between two quantitative variables, here the invoice amount and the time spent on site, with the different dots colored according to the origin, according to a qualitative variable, so Earth, Mars, or Pluto. From this scatter plot, we're able to state many things. We're able to say that invoice amount decreases with time spent on the website. We're also able to say that Plutonians spend more money on the website compared to the others, that Martians and humans form a relatively homogeneous group, and we are able also to say many other things. So we had some kind of an exploratory reasoning on this simple chart. All of these are hypotheses we will be able to test using statistical testing. So we had exactly the same kind of reasoning, but on a higher number of variables using exploratory data analysis. So that was the topic of the second webinar, in which we talked a lot about this specific tool, which is a dimension reduction technique, which is called PCA, or Principal Component Analysis. So PCA also allowed us to have this kind of reasoning, to generate this kind of statements or hypotheses. We were able to say that weight and height were positively and strongly correlated. We were able to say also that shoe size is unrelated to weight and height, and to say that time spent on the site is negatively correlated to weight and height. So we interpreted things in terms of angles. Then on the observation plot of the PCA, we noticed that there were two clusters appearing. Our customers are split into two groups, or two segments. One segment is associated to high weight and important height, and less important time spent on the website. And the other group is the opposite. So low height, low weight, and important time spent on the website. And there were specific outliers. So Derek and Sean, who had important shoe size for Derek and low shoe size for Sean. So here are our PCA explorations or hypotheses. Today, with statistical testing, we'll be able to test the validity of this kind of statements or hypotheses. So today we start our reasoning with a very specific question. Is this hypothesis valid or not? Statistical tests allow us to accept or to reject a very precise hypothesis, assuming error risks. So statistical tests usually answer questions whose answer is yes or no. So here's a step framework I can propose to you. This is the steps I personally follow to run statistical tests. So you can adopt it if you like it. Here we go. First of all, we write the question whose answer is yes or no. Then second step, which is very important, we write the null and the alternative hypothesis linked to this question. We'll see what the null and the alternative hypothesis are later on. Then we choose an appropriate statistical test that will let us address those hypotheses and an appropriate alpha risk threshold. So to choose the appropriate test, you can check out our guide online by clicking on this link, the guide I showed you earlier. We'll see what the alpha risk threshold is as well. Then we gather the data. Then we run the test on the data. And the test allows us to answer the question using a number called p-value. So if the p-value is lower than the risk alpha we defined here, we reject the null hypothesis with a risk that is proportional to the p-value of being wrong. Then we'll add things here a bit later. You'll see what. So we'll take one specific question and address all of these single steps to finally answer the question using a statistical test. Let's go. First of all, we start with a question. Do fertilizers A and B induce a difference in sugar rate or sugar concentration in bananas? So the question is quite straightforward, I think. Step 2, we write the null and the alternative hypothesis. So now we'll discover what are those hypotheses about. The null and the alternative hypothesis. Here's our question. First of all, the null hypothesis, that's also written as H0, it generally implies an idea of equality. Here's the equal sign. In our case, we would write the null hypothesis this way. So the mean sugar rate in A fertilized bananas equals the mean sugar rate in B fertilized bananas. The null hypothesis is challenged by an alternative hypothesis, an opposing hypothesis, which is called the alternative hypothesis. It generally implies an idea of difference. So one of the ways to write an alternative hypothesis is like this. The mean sugar rate in A fertilized bananas is different from the mean sugar rate in B fertilized bananas. So starting from our question, we write two opposing hypotheses. The null hypothesis that implies an idea of equality, opposed to the alternative hypothesis that implies an idea of a difference. So where are we so far? Here we are. So we have written the question, the hypothesis. Now it's time to choose the appropriate statistical test to address those hypotheses, as well as the alpha risk threshold. So what are we doing basically? If we look back at those hypotheses we just wrote, are we comparing means? And if such, how many? Are we comparing proportions? And if such, how many? Are we comparing variances? And if that is the case, how many? Are we testing associations between pairs of variables or between blocks or inside a block of variables? And on and on. So in our case, we are comparing two means. According to our statistical guide online, the student's t-test for two independent samples would be appropriate. Then, choosing the alpha risk threshold. What is the alpha risk? The alpha risk threshold is the risk below which we decide to reject the null hypothesis. It's a number that is bounded between 0 and 1. And it's a very important threshold below which we decide to reject H0 if the p-value is ever lower than this risk. So we'll see what the p-value is. The more we want to limit the risk of taking a wrong decision, the more we should decrease alpha. And the more severe you want to be with yourself, the lower the alpha risk threshold should be. So it all depends on the severity you want to have in taking the decision or not. So do you prefer not taking a decision at all instead of taking a potentially wrong decision? in this case, you should lower the alpha risk threshold. If the consequence of taking a wrong decision is not so bad, then you can increase the alpha risk threshold. So it all depends on the question you're asking and on the subsequent decision you want to make. People often set alpha at 0.05, so this is not a reason to do it systematically. So you should really think well about your alpha risk threshold before setting it, and not go directly on a systematic 0.05. But this is what we're going to do in our example. Step 4, gathering the data. So we set up an experiment with 60 banana trees. 30 of them receive fertilizer A and 30 of them receive fertilizer B. So we gather the data in Excel and then we plot them. We gather sugar concentration in each of the trees and then we plot the data like this. So here we have sugar concentration of fertilizer of banana trees submitted to fertilizer A compared to banana trees submitted to fertilizer B. Obviously, according to this chart, we might say that the bananas submitted to fertilizer B have a higher sugar concentration in their fruits. The statistical tests will allow us to see if this difference is statistically significant or not. So step 5, running the test in XLSTAT. So here's the data set. We have 2 columns and we have 60 rows. Here each row represents one banana tree. And the first column is the fertilizer, the second is the sugar concentration. As you can see, there are 30 trees submitted to fertilizer A and 30 trees submitted to fertilizer B. Here we are in Excel, and this is XLSTAT, so it's a statistical software that gets integrated into Excel. It's not onto Excel. We have different statistical features that are can be accessed through those menus. So students t-test for 2 independent samples can be accessed right here. So 2 sample t-test and z-test. I'll click on it, so under the parametric tests menu. There are many data formats we can have. Can either have 1 column per sample or 1 column per variable. So this is the case here. We have 1 column per variable. The data should be captured here. And sample identifiers, so the treatment that identifies each banana tree should be selected right here. Then there are many things that can be configured in the options. Here, notably, we have the significance level. This is the alpha risk threshold that is expressed in a percentage here. So 5% means 0.05, an alpha threshold of 0.05. So you can change it as you want. You can set it to 1, to 5. It's up to you. Then there are many things also you can configure in the outputs and in the charts. I click on OK as soon as I'm ready. And I get the result here. We'll focus on 2 very important numbers, the p-value, as well as the threshold alpha we previously chose, so 0.05. So I'll comment on this on my presentation. Here we are. So we just ran the test on XLSTAT. Now it's time to interpret the result and answer the question. So the decision is made by comparing the p-value to the risk threshold alpha we set earlier. Here's the question again, the null hypothesis and the alternative hypothesis. The test computes a number called p-value, we just saw. The p-value is a probability value, so it's also bounded between 0 and 1. The p-value should be compared to alpha. It's the risk you take of being wrong when rejecting H0 and accepting HA. So if p-value is lower than alpha, we reject H0 and accept HA, assuming a risk proportional to p-value of being wrong. In our case, if you remember, the p-value was lower than alpha. It was very small. So in our case, we can reject this null hypothesis, reject the hypothesis of equality between fertilizers, and accept the alternative hypothesis, so the idea of a difference between the two fertilizers, difference in mean sugar rate. So in our case, the p-value is lower than alpha, so we can reject the null hypothesis and accept the alternative hypothesis, and we're taking a risk of being wrong that is proportional to the p-value. So here we go. Those are the results we just saw. The p-value is super low, and the risk threshold alpha is here. You have a test interpretation that appears in XLSTAT as well. So this is another way to formulate the H0 and HA hypothesis. So the p-value is lower than alpha. We reject H0 and accept HA with a very low risk of being wrong. So the answer to the question is the two means of sugar rate for fertilizer A versus fertilizer B are significantly different. So now we switch to one of the oppositions we find in the statistical tests world, parametric versus non-parametric tests. We often hear about parametric and non-parametric tests. It's all a matter of the opposition between power and robustness. Before carrying on, maybe I can take your questions. Should you run a normality test on your data before you analyze your data? In your banana fertilizers example. Yes, we're going to talk about normality just now with parametric versus non-parametric tests. If you check out this guide, here's the t-test on two independent samples. And you have the conditions of validity of this test, which is parametric. Those are the conditions. So if you go down, here they are. So the measurements should be independent. Samples should have equal variances. You should have at least 20 individuals per sample, or the normality of the population of every sample verified or assumed. So you either assume that the populations from which your banana samples are extracted follow a normal distribution, or you should verify this normality through a normality test, for example. And if your sample sizes are high enough, so above 20, or some authors also say above 30, then there's a statistical theorem that says that the normality assumption is not important anymore. So what about the z-test? Here you have an option to use the z-test also. The z-test can be used when you know the population variances, the theoretical variances of your samples. So you have samples of 30 banana trees. If you have the theoretical variances or standard deviations of the populations from which the samples were extracted, here you can use a z-test, but this is rarely the case. You rarely have access to the theoretical variances. So in this case, if you choose z-test, you can enter the variances in the dialog box. So now we talk about the opposition between parametric and non-parametric tests. It's a matter of opposition between power and robustness. So a statistical test can be either parametric or non-parametric. Parametric tests are reliable only under certain conditions that are linked to the distribution of populations. That, as we just saw, there are assumptions on normality, for example, and on the variances that should be validated, or that should be verified before running the tests. So these conditions can be found in our online statistical testing guide that I just showed you. So parametric tests, such as the student's t-test for 2 samples, are only reliable under certain conditions. Whereas non-parametric tests are more universal. They can adapt to a wider range of situations. They do not assume any underlying distributions, and most of non-parametric tests are computed from the ranks of the data. So non-parametric tests are more general, are more universal, and parametric tests have their non-parametric equivalents. So one question you may ask is, why do we still use parametric tests and bother ourselves in testing the assumptions and verifying assumptions? Why don't we just systematically use non-parametric tests? So the answer to this question is in the following slide. So non-parametric tests, as I just told you, are reliable in a larger number of situations than parametric tests. They are more robust. So the robustness, the definition of robustness is this. So they are reliable in a larger number of situations than parametric tests. In opposition, parametric tests are more able to reject H0 if it's wrong and if applicability conditions are respected. So we say they have a higher statistical power. So parametric tests have more power than non-parametric tests. Well, usually, in most of the cases, we try to reject H0. So parametric tests have a more power to reject H0 if it's false compared to non-parametric tests. So this is called simply statistical power. So non-parametric tests are more robust and parametric tests are more powerful. So if one has the chance to use parametric tests on the data they have, then it's good. Otherwise, a solution is to take non-parametric tests. So here's a framework on how to do things. It's just a proposition. You can choose an appropriate parametric test when everything is already set, the null hypothesis and everything. You gather the data. You ask yourself, are assumptions for the parametric tests met? If so, you run the test and you answer the question. If not, you can replace with a non-parametric test, which is less powerful, but which is more robust. Then second opposition I wanted to tell you about is the tests on independent samples versus tests on paired samples. It's all a matter of a number of populations that we are working on. So in independent samples, we have 2 or more distinct populations. For example, when you compare a treated group and a control group, or when you compare females and males, or when you compare treated and untreated banana trees, or trees submitted to fertilizer A and trees submitted to fertilizer B. So you have the individuals, each individual cannot be found in more than one sample or more than one group. So we don't have, in our example, we don't have any banana tree submitted to both fertilizers. Whereas paired samples imply one single population. For example, you measure the weight of patients before and after a treatment, and you try to investigate the effect of time or the effect of the treatment, sorry. And then you can also follow up companies or surveyed individuals at different dates. So you investigate the effect of time. You can also follow the photosynthetic capacities of the same banana trees at different dates or at different times of the day. So here also you are investigating time. It's always the same population you are measuring, in the same set of patients or of trees or of plants or of animals. So this is the main difference between both. And there are tests that are adapted to independent samples, and there are other tests adapted to paired samples. So we talked about the opposition between non-parametric and parametric tests, the opposition between paired and independent samples. Now I will talk to you about the opposition between comparison and association tests. Comparison tests let you compare things such as means. The student's t-test that we just saw allow you to compare two means. ANOVA allows you to compare more than two means. Comparing variances, you have Fisher's test that helps you compare two variances, Levin's test that compares more than two variances. You can compare proportions, and there are many other comparison tests. You also have variable association tests that let you test the association between two qualitative variables, for example, like the chi-square and exact Fisher's test, and also test the association between two quantitative variables, the test on Pearson and Spearman correlation coefficients, for example. So next step, now that we have talked about all of these different oppositions in the world of statistical testing, I can show you this table that integrates the information from all of these oppositions and allow you to choose one appropriate test according to your situation. So it's a subset, if you want, of the more global grid you have online. So here you have comparing two means. Are your samples independent or paired? Here are parametric tests and non-parametric equivalents if the conditions of validity are not respected here. Here's a reminder of the link to the bigger grid online. And before concluding, I will run one last test in XLSTAT, one association test between two qualitative variables. I want to investigate the significance of a contingency table or a crosstab. We saw contingency tables in the first webinar on descriptive statistics when we wanted to investigate the description of the link between two qualitative variables. So here we'll play with this data set. It's a customer satisfaction survey from a car garage. Here once again we have surveyed people in rows and the questions we ask them in columns. We have also in addition the socio-professional category. We ask them if whether they were satisfied by the garage service and whether their car was repaired, and how they rate the welcome of the garage, and are they satisfied by the ratio between quality and price, and would they come back? Yes, don't know, or no. Now our goal, the question we ask, is the answer to the comeback question linked or dependent on the social professional category? Is there a link between those two variables? So here's how we run things in XLSTAT. So before doing so, I want to show you another way of representing the data, which is the contingency table, which we already saw in the first webinar. Here we have the social professional categories in rows, so A or B. We have the answers to the comeback question in columns, so no, yes, or don't know. And here each number is the number of persons who correspond to the corresponding categories. So here we have 5 people who are part of social professional category A and who answered no. We have 1 person answering yes from the category B. Here's another way to represent things. So we have the percentages of A's and B's for each of the answers. Now the null and the alternative hypotheses here we are investigating are those. So proportions of categories A and B do not change according to categories no, yes, and don't know. And in opposition, proportions of categories A and B change according to categories no, yes, and don't know. So here, if you see here the proportions, which are expressed in percentages, you can see that there's a big difference between no yes and no no's. If you switch from no to yes, you have a big difference between 45 and 75. So we may expect, according to the data, that we have a very low p-value, that we reach a very low p-value that would reject the null hypothesis that the proportions are equal. So let's see what we get in XLSTAT. So here's the garage dataset. I'll go to correlation and association tests and click on tests on contingency tables. Here in the row variables, actually there are two data formats in the dialog box. You can either have qualitative variables, which is our case, or already have your data in the form of a contingency table or a crosstab. So here I'll keep this data format. I'll take the social professional category in the row variable field and the comeback question in the column variable field. In the options tab, there are many tests we can have. They all answer more or less the same question, or they are all related to the same hypothesis, the same null and alternative hypothesis. There's the chi-square test, which is the most famous one. There's Fisher's exact test, which is non-parametric, so which is very robust. We also have the Monte Carlo method, which is robust as well. So we try to stick on the Fisher's exact test, which is non-parametric, because the chi-square test has conditions of validity that you can check online on the guide. Here also there are many outputs we can play with, and I click OK as soon as I'm ready. Here we go. Here's Fisher's exact test and the alpha threshold that I didn't set in the dialog box, but I could have done this. 0.76. This is not what we expected according to what we saw in the data. So we expected a p-value that is far lower than the alpha risk threshold, but we got a p-value that is super big. How can we interpret this? How can we interpret the opposition between what we expected from the data and the p-value we got? Well, first of all, as I told you, the non-parametric tests in general are not that powerful. They lack of statistical power. So they lack of their capacity of rejecting the H0 hypothesis if this hypothesis is wrong. Then second and most important thing is sample size. Statistical power, or the ability of a test to detect or to reject H0, really depends usually on sample size. Here if you see, there are very few people who responded to the survey. The sample size is very low, so the p-value is very likely to be insignificant or to be very, very big. Usually when you have larger sample sizes, you get more chance of detecting, of rejecting H0 if H0 is wrong. So this is the main reason, I think, why we got this p-value, which is very high compared to what we expected according to the results. So p-value is higher than alpha. We cannot reject H0. We cannot take any decision, actually. There's an appendix in the presentation, that tells you how to interpret p-value and is there any way we can accept H0. So everything is detailed in the appendix. I will let you have a look if you want. So here we revisit the steps I showed you earlier and we take a conclusion. So we start usually with writing up the question. Then from the question we write the null and the alternative hypothesis. From this we choose an appropriate statistical test and an alpha risk threshold. We gather the data. We ask ourselves, are the assumptions for the parametric test met? If that's the case, we run the test, and we answer the question. So if p-value is lower than alpha, we reject H0. If not, we do not reject H0. If the assumptions of the parametric test are not met, one solution would be to replace the test with a non-parametric equivalent, which is less powerful, sure, but which will be reliable at least. It's more robust. So here's the conclusion. Statistical tools can be stored into 4 categories. You have description, exploration that allow to generate hypotheses. Tests, statistical tests allow us to test those hypotheses. And we'll see in the upcoming webinars that modeling allows us to understand the way a phenomenon evolves according to a set of parameters. So we've already done webinars on those 3 topics, and I really hope that I will be able to talk to you again in the upcoming webinars. So thank you very much for attending. I'll answer the remaining of questions now. Okay. If you have data that you are collecting from a homogeneous population, from one single population over 6 months, to run a test to compare their answers during the first 3 months versus the second 3 months, you should use the paired sample methodology. Yes, so the answer is yes. So you have one single population you are following over time. Of course, you need to choose a statistical test that relies on dependent samples. Is there a tool to evaluate if it is possible to do a parametric or non-parametric test? Well, you have suggestions in the statistical guide I showed you to check or to diagnose your data to see if you can apply a parametric test. And if not, one of the solutions would be to switch to a non-parametric test. Now, this is not the only solution you have when the parametric assumptions are not met. There's another solution which is very interesting and which is used by many people. If your data do not match the parametric assumptions, you can transform them using functions such as the logarithm or the square root. And those transformations allow your data to get closer maybe to normality or to the assumptions in general, to test parametric test assumption in general, and let you run the test anyway, the parametric test, without having to switch to a less powerful test, which is non-parametric test. So you can try transforming your data, and if your data get closer to the assumptions, you can run your test anyway on the transformed data. Hello, I wanted to know the best method for comparing several annual rates. Well, it depends. If you are following the same objects or the same individuals across time, then you have, I go on the guide, you have specific methods that let you do this. Here we go. Compare several observed means, dependent measurements. You have repeated measures ANOVA and mixed models, and you have non-parametric equivalents, and here are the assumptions. So if you are following the same objects over time, those are appropriate methods you can use. What are the conditions for testing correlations between 2 quantitative variables? Well, the conditions for parametric tests is that each sample follows a normal distribution, so the Pearson correlation coefficients, for example. Otherwise, you have Spearman's correlation coefficient, which is non-parametric, and the associated test is non-parametric as well. Soil with different treatments would be independent samples. Yes, if you have a series of soils that are submitted to one treatment and another series of soils that are submitted to another treatment, and you are asking yourself whether there's an effect of the treatment on soil fertility, for example, yes, you'd be in an independent scenario. What can be done in order to gain powerful in the non-parametric test? Well, there are many ways to get more powerful in your data or in your test. You have this in your appendix, how to increase statistical power. So statistical power increases with the number of measurements, number of repetitions you have, the measurement precision, if you avoid doing precision errors, the size effect, so the expected difference between treatments, the alpha threshold, so if you increase your alpha threshold, you are more likely to reject H0, this is quite logic, and the statistical test used, so parametric or non-parametric. How can you transform the data to meet the assumptions? So here, if I take the bananas examples, so let's say the banana examples doesn't meet the assumptions. You can create another variable here, which is the log transformed sugar rate. You can use the Excel functions simply like this and create this data like this, and you can run your test on these data if they ever meet the parametric assumptions. You can run the test on these data and the result will be reliable. Can correlations help knowing the depth of the association between two variables? If not, how can we quantify the association between variables? Yes, the correlations are the most popular tools used to investigate the depth of the association between variables, and then you can have correlation coefficients and associated p-values, letting you know whether those coefficients are significantly different from 0 or not. So if you see here in the guides, the association tests, if you want to test the association between two quantitative variables, here's the null hypothesis. Variable 1 and variable 2 are independent, and another way to write down this null hypothesis is to say the correlation coefficient equals 0. So here we are challenging the null hypothesis that the correlation coefficient is equals to 0. What is a reliable sample size to perform this kind of test, a t-test for example, and why? Well, you have one whole tool in the power analysis module, which is part of some of advanced statistical solutions in Excel, that allow you to know the size of the sample you need to have in order to obtain an appropriate statistical power prior to launching your experiment. So if you want to compare means here, you can find the sample size for one sample t-test or t-test for two paired samples or two independent samples. And you choose the alpha threshold, the power you want to have, and then there are other parameters you need to fill in before computing the sample size that will allow you to have the target power. How can we test the normality of a variable? So here we have, there are many ways, but one of the most popular ways is to launch a normality test. Test the normality of a series of measurements. You can simply click on this, and you have one whole tutorial that shows you how to test normality using XLSTAT. If data are parametric, but we're looking at the same sample over time, let's say a couple of years, is ANOVA appropriate? That would be paired. That is the right tool. Well, you have adapted ANOVA methods for this kind of data. You have repeated measures ANOVA and mixed models. Do you have any way to check if parametric assumptions are met? Well, you need to do it by hand. And you have all the instructions in the statistical guide. Well, thank you very much, everyone. We're running out of time. I was very happy talking to you today, and I hope to see you in the upcoming webinars.